Lesson 3.5 deals with linear programming, and this is an application of solving systems of inequalities. So you can read here, linear programming is a technique used to maximize or minimize a particular quantity represented by an objective function. So there'll be some equation or function that we want to find the highest value or the lowest value if possible. And we want to do this under a given set of inequalities, and those inequalities, or that group of inequalities, the system of inequalities, are called the constraints. And we're going to use this vertex principle of linear programming, which says if there is a maximum or minimum value of the function that we're talking about, it occurs at one or more of the vertices of the feasible region. So the feasible region is going to be the solution of the system of inequalities. So as we remember, we can graph inequalities and see where all those shadings overlap. Where all of them overlap is going to be called the feasible region. So we're going to just start off with a simple example here. Later on, we'll get into ones that actually involve actual word problems. Find the ordered pairs that will maximize and minimize the objective function z equals 3x plus 5y under the given constraints. State the value of the function at each point. So right here, it's dealing with x values, so 0 is less than or equal to x, which is less than or equal to 4. That means all of our x values are between 0 and 4. It's got the or equal to there, so we use a solid line. And so that's what we will do. We'll take this, we want it greater than 4, or sorry, greater than or equal to 0, which is right here, the y-axis actually, and less than or equal to 4, which is right there. And now let's go ahead and look at our next system there, our next set of inequalities, and this says y is less than, or 0 is less than or equal to y, which is less than or equal to 2. So that means our y value it's not what I wanted to happen, is greater than or equal to 0 and less than or equal to 2. And so these represent the first two constraints. Move this down into place. Then we have this one, this x plus y is less than or equal to 5. Let's go ahead and put that in slope-intercept form, so we would subtract x from both sides. And that would give us y is less than or equal to negative x plus 5. And we know this is a line that goes through 5 on the y-axis and has a slope of negative 1. So we can think of that as negative 1 over 1. So down 1, right 1, down 1, right 1, and here's the slope. And then we have that line. Again, this is greater than or equal to, so we have a solid line. Would look like this. Now, I didn't do any shading yet because I didn't want to make it too messy here, but what we have here, we're between the two blue lines because of this, between the red lines because of this, and so that would be that rectangle there, and then this is less than or equal to, so below this black line. So it's actually this shape right here that is this solution to that system of inequalities. And now what we want to do, now that we found the solution, this is called the feasible region, this shaded area here. We want to find the vertices of this shaded region. So what are the vertices here? Here we have 0, 0. We have 4, 0. That's this point here. We have 4, 1. This point here is 4, 1. Up here to this point here, this is 3, 2. And our last point right here is 0, 2. So the idea is we graph our inequalities, we find the feasible region, we list our vertices, And then what we do is we plug each vertex into our objective function. So in this case, we want to find the highest value of z and the lowest value of c. So we put 0. This is our x value. So these are all x comma y. So we're going to put 0 in for x and then 0 in for y. So we're going to put this one in. We have 3 times 0 plus 5 times 0, which obviously gives us 0. This one, we have 3 times x, so 3 times 4, plus 5 times y. Well, our y value is 0. And so this is 12 plus 0. 12 plus 0 is 12. Next one, we have 3 times our x value, so 3 times 4, plus 5 times the y value, 5 times y, and our y value is 1. And so this ends up being 12 plus 5, which is 17. Our next one is 3 times our x value, which was 3, plus 5 times the y value, in this case is 2, equals 9. 3 times 3 is 9, plus 5 times 2 is 10, which is 19. And then we can put in the point 0, 2. So again, we're putting in this function, 3 times 0 plus 5 times 2. And this is 0 plus 10, which is 10. Find the order pairs that will maximize and minimize. Well, the order pair 0, 0 minimizes. That's the lowest. Let me mention this. That minimizes because that's the lowest number here. So what we're doing now is we're looking at 0, 12, 17, 19, and 10 are minimum. So the 0, 0 minimizes the function. Which one maximizes the function? Well, 19 is the maximum, so 3, 2 maximizes the function. And so that's what you do. You graph your inequalities, you find your feasible region, you state the points that are the vertices of that feasible region, and then you plug it into the objective function. Let's take a look at another one. X is greater than or equal to 0. This is a good one just to talk about really quickly. X is greater than or equal to 0. So this is just saying we want above the y-axis. So, sorry, to the right of the y-axis, we want things to the right above 0. So we want things greater than 0. For the next part, for this part, we want y is greater than 2. So here's 2. We want y is greater than 2. So as of right now, we have to the right of the red, above the blue, so this region up here, but we still have 2 more here that we want to work with. Let's do this one in green. So that's x plus y is greater than or equal to 4. We would subtract x from both sides to put this in slope-intercept form. We've got negative x plus 4. So we have a y-intercept of 4, a slope of negative 1 again. So we go down 1, right 1. So we have this here. Now we have to think about our inequality. It's greater than, so it would be above. So right now we're above the blue, above the red, or above the green, and to the right of the red. And now we have this last function here. We can do that in black. And so we have 3x plus y is greater than or equal to 6. Subtract 3x from both sides. And we get y is greater than or equal to negative 3x plus 6. So here's 6. Slope of negative 3, which we can think of as negative 3 over 1. So we go down 3, right 1. Down 3, right 1. So that line is here. Let's just come up here and use a line. and it is a greater than sign, so it's above there. So the area we're looking for here is actually not closed in because it's greater than all these values. So it's to the right of the red, above the black, above the green, and above the blue. And so it's this region all out here. I'm not going to be able to color it in all the way, but it's everything out here. Well, this could present a problem because it's not a closed-in region. So there might be a maximum or there might be a minimum, but there's probably not going to be both because this extends forever this way. And you might think, well, it's always going to be, there's definitely no maximum, which in this case it is, but you really have to go back to your objective function. These are both positives, a positive 5x and a positive 2y. So as these numbers grow, get larger, this will definitely get larger. But if these were negatives in here, it could be possible that there's a minimum. I mean that there's a maximum but no minimum. So what we want to do now is we want to check our vertices. So we have just 3 vertices here. We have 0, 6 is this one. And then we have, let's come down here, this is 1, 3. And then we have 2, 2. Hopefully I left enough room here. We're going to put each of these points into our function. This is written a little differently, but it's the function on x and y is 5x plus 2y. So we're going to plug in 5x plus 2y. So 5 times x, which is 0, plus 2 times y, which is 6. 0 plus 12 equals 12. This next one is going to be 5 times x, so 5 times 1. Plus 2 times y, so 2 times 3. Thinking through this, this is 5 plus 6 is 11. And then our last one, we have 5 times x, which is 2. And y is also 2, so 2 times 2 is equal to 10 plus 4, which is 14. And so we see our minimum would be at 1, 3. These are both higher. Now, you might say this is a maximum, but let's just pick a number out here, like 7, 3. If you put 7, 3 in here, obviously this is going to be larger, so 5 times 7. 5 times 7 plus 2 times 3. That would give us 35 plus 6 is 41, obviously larger than 14. So these numbers up here, they keep getting larger and larger. So there's a minimum of 11 at the point 1, 3, but there's no maximum.